Great. Thanks to the organizers for making this happen. I'm not the original speaker. If you don't like my talk, you should blame the French visa authorities. So I'm the substitute. And I'm going to tell you about something related to quantum error correcting codes, which have a certain algebraic flavor that hopefully you'll find relevant. And one property of quantum error correcting codes is related to the property of ground states of local Hamiltonians, and I'll explain later why these are very closely related, is that code states are very entangled. And so this is something that we see in nature, is that the ground states of physical Hamiltonians are entangled. But how robust is this entanglement? In other words, if we allow a small amount of error, can we describe the system pretty well without entanglement? If so, then a lot of the difficulties of analyzing quantum mechanics could go away if we want just an approximate picture of things. So I'm going to describe today a construction of a Hamiltonian with robust entanglement. And I'm also going to talk more broadly about the goal of robust quantum error correction, something called a locally testable quantum code. So I'm going to talk first actually about classical error correction and classical locally testable codes, the classical PCP theorem, and then that's as motivation for their quantum analogs, and then I'll talk about our construction of a Hamiltonian whose ground states have robust entanglement. It's all joint work with Lior Eldar, and it's on the archive here, although it's more recent than you would think, because the first version was very wrong, and the recent version is more like a year old. Okay, so let me first tell you about classical codes. And as a warning, by the way, everything in this talk will be finite dimensional and, even worse, basis dependent. So apologies in advance. So a classical NKD code is a subset of n-bit strings. So f2 to the n, that's my way of saying n-bit strings, because we'll occasionally want some of the field structure. So the idea is that I have k bits that I want to transmit, and I'm going to encode them with some redundancy so I can correct for errors into n bits. So the fact that I am encoding k bits means that this set should have size 2 to the k. So there are 2 to the k possible messages, each of which is encoded as an n-bit string. And then the error correction property is expressed by this third parameter, the distance. So d is the minimum over points in the code that are not equal of the distance between these points. And by distance here, I mean the one norm, the number of positions in which they differ. So if I have a code where, so the distance means essentially the geometry of the code looks like this. You know, I have points that are far apart, and so if I get some corrupted version of one of the code words, let's say this green point right here, if there are not too many errors, then I can uniquely reconstruct the closest code word that it came from. So I can correct up to d over 2 errors. So I'll give you a few. So one easy example of a code is the repetition code. So the repetition code means the simplest code you can imagine. You just have 2 code words. One of them is you repeat 0 n times. The other one is you repeat 1 n times. It's a very simple code. It encodes 1 bit, and the distance is n, right? These points are as far apart as they could be. It's, you know, the best way of correcting errors if you don't mind having a very bad rate. And this is really what all of our classical computers run on, right? So if you have a transistor and there's current flowing either one way or another way, the current involves many electrons. And so you have maybe billions of electrons going down one path or billions of electrons going down another path. Or in a hard drive cell, you have billions of magnetic spins aligned one way or another way. I guess it's less than billions now, but thousands at least. And so the difficulty of quantum error correcting codes is that we don't have a code as nice as the repetition code that we can use as sort of the basic building block of quantum computing. So the repetition code is great for distance. K is not so good. Of course, if I just take C to be a random set of size K equals 2 to the alpha n, where alpha is some number between 0 and 1, then it's not hard to show that the distance will be 2 to the beta n for beta some function of alpha with high probability. So I'm not going to write down what that function is. It's a nice exercise to work it out. It involves entropies. But if this says that if you choose a random code, then you'll have what's called linear rate and linear distance. The number of encoded bits is going to be alpha at, sorry, this is k, sorry, 2 to the k equals 2 to the alpha n. So k, the number of encoded bits, is a constant fraction of n. And the distance is also a constant, I'm really, beta times n. The distance is a constant fraction of n as well. So you can correct a constant fraction of errors and encode a constant fraction of the bits at a constant rate. So this is nice in theory, but it's very hard to work with on a computer, right? So to write down this list of random points is really infeasible. Your code book is exponentially large. So you'd like to describe the code in a more succinct way, one that's more amenable to, for example, doing this maximum likelihood decoding. So if you want to find the nearest code word, you'd really like a more succinct description of the code. You'd like other things as well, but at a minimum, you need a more succinct description. So one very important class are linear codes, in which the code space is a linear subspace. And usually we write this as the kernel of some matrix. So this matrix is just some m by n matrix. We can think of the rows of the matrix as checks. So saying that we're in the kernel of the matrix means, so if x is in the kernel of the matrix, that's the same as saying that it has 0 inner product for each row. So these lowercase a1 through am, these are the rows of the matrix. Saying we're in the kernel means we have 0 inner product with each row. So these you can call the checks of the code. So saying you're in the code means that you pass all of these parity checks. So let's see. Nope. Good. So for example, the repetition code, we might take A to be the matrix and these correspond to constraints right? So if you satisfy all of these constraints, that's equivalent to being in the repetition code. And there's one nice property of these, and by the way, one important thing to realize is that the number of checks, so I won't write that up there now, we can have m the number of checks should be generically greater than or equal to n minus k. So you can have linear dependencies among your checks, and there can be reasons why that is advantageous, which we'll return to. So in order to make codes practical, it's helpful to have them be linear. But there's actually even more features that are often desirable. One of them is to perform these checks, we would prefer not to examine too many bits. If each check only has to look at a constant number of bits, that would make the decoding of it more efficient. So this is called, there's going to be a lot of acronyms. This is called a low density parity check code. Doesn't even matter what it stands for, but it has the property that each AI has constant weight. So this is a further desirable property of codes, which we would, which often helps in practice. And now, this is, okay, so this is all I want to say about coding, about how to protect information. There's one important thing which is missing here, which is robustness. So to be in the code space, what it means is you satisfy all of the checks. But what if you just satisfy most of the checks? Is there any kind of guarantee you can get in that case? So there are a few reasons why this might be helpful. One of them is, suppose you want to very quickly verify if you're in the code or you're far from the code space. It'd be nice if you could just sample at random a few of these checks, and then you could very quickly make this determination. Otherwise, you have to check. You have to go through everything. You have to go through the entire parity check matrix. So there's one further property that people ask for in codes. LTC means that it's a locally testable code. So this is locally testable code. And the property, so this is now, and you'll notice this LDPC condition is basis dependent. This locally testable code condition is also basis dependent. And here, you'll see it's crucial that the number of checks be larger than you would need. So the locally testable code condition is that not only can we do these checks by examining a constant number of bits, but we can also, if we're far from the code, it will show up in many of the checks. So if we're far from the code, if let's say we have a large fraction of our positions are far from any code word, then a large fraction of the checks should also be violated. So we can say, in other words, for any x, the probability over a random check that is violated should be at least some constant delta times the fractional distance. So this is the distance of x to the code space divided by n, so now it's a number between 0 and 1. It's the fraction of positions where I differ from the closest code word. And delta is just, well, it's a property. How good of a LTC you are depends on how large delta is. In general, we can at most hope for it to be a constant. And because this is sort of a fraction, and this is also a fraction. And this says, if you're a delta robust locally testable code, and you differ in some fraction of positions, then that times delta is the chance that a random constraint will notice that you are that you're not in the code. So as an example, let's look at the repetition code. And you can see the way I've written it, it is not at all locally testable. At least, or everything's locally testable with some bad delta. And this achieves a delta that goes like 1 over n. Because you can just take x to be n over 2 zeros and n over 2 ones. Your distance from a code word is large, half the positions. You differ in half the positions from any code word, but you only violate this one check here. So delta is on the order of 1 over n if you have the repetition code with these checks. So the repetition code, I said that in terms of distance, it's as good as you can get, but it's very not robust. You violate one constraint, you can be very far from any code word. So I pointed out this is a basis-dependent property, and the repetition code can be locally testable if you use a different set of checks. And they can still be weight 2 checks. So they can still be checks on pairs of bits. What we'll do instead is we will, the checks will be xi plus xj equals 0 for all ij corresponding to edges of some graph. Okay, and we'll take this graph to be a, let's say, a 3 regular expander graph. So 3 regular means every vertex is degree 3. Expander graph means that if you have pick a random edge and sorry, I forgot to say, sorry, let's say that S is a subset of vertices, and the size of S is at most half of the number of vertices. So there are n vertices. You have a subset of at most n over 2 of them. Now I'm going to pick a random edge, and I ask, conditioned on one point of this edge being in my set, what is the probability that the other point is outside of that set? So, here's my graph. And then let's say S are these 3 vertices. If I choose an edge, there's some edges entirely within the set. There's some that leave the set. What is the probability that if I choose one endpoint in the set, that the edge is leaving the set, that the other endpoint is out of the set? So this is called the expansion of a set S. And the expansion of the entire graph is the minimum expansion of any set of at most half of the vertices. We'll see there are a few reasons why half is natural. One sort of obvious reason is if you took the set to be all of the vertices, then this probability would be 0. Or if you took it to be almost all of the vertices, the probability would be almost 0. So there's it's kind of a trivial reason why it can't be too large. But there's a generalization which also makes it clear why this should be the right thing. So an expander graph has a property that this is lower bounded by a constant. And this expansion condition is exactly what you need for the repetition code to become a locally testable code. So why is that? Let's suppose that x is 0 in positions S and 1 in positions that are the complement of S. And without loss of generality, let's suppose that S is less than n over 2. Then the number of edges that go between these two sets is a constant fraction. So let me say the distance of x to the code is going to be the size of S. And the number of violated edges is going to be the size of S times the expansion of S. Maybe there's a constant like 2 also. So if this expansion is constant, then the number of violated constraints will be proportional to the distance. And we'll have that choosing a random constraint has a a good chance of detecting that you're not in the code. So you'll have a good chance of picking an edge between the 0 set and between the 1 set. Any questions about this so far? So let me, OK, this is tableau 2. Good. Great. I'll mention one generalization of this, which will be useful later on. Which is, you can think about these codes in terms of homology over F2. So suppose I have some simplicial complex with vertices, edges, faces, and maybe beyond. I can associate a vector space with each one. So let me write F2 to the V means if I, the vectors that assign 0 or 1 to every vertex. And similarly for the edges and the faces. And then I can have boundary maps between them. And so this matrix A is going to be the boundary map from V to E. And the expansion is just the minimum over X not in the kernel of A of the one norm of AX. So the kernel of A are the things that are annihilated by this map. So in basically the connected components of the graph. And so for the repetition code, the kernel of A is just the all zeros vector and the all ones vector. And so the things that are not in the kernel of A are the things that are not in the code. AX is a set of violated edges. So all the edges that are not, where the two endpoints don't agree, this counts the number of those edges. And then you divide by the distance of X to the kernel. This says if I'm this far away from the kernel, the further away I am, the more detectable it should be. And so this ratio is like a measure of expansion. And now we see we don't have this n over 2 condition anymore. The n over 2 condition is replaced by just the distance of X to the kernel. Right? So if the weight of X is less than n over 2, this is just the weight of X. If the weight of X is more, you just replace X with its complement. And so this is, I think, a natural generalization of expansion. And one open question is, can we continue having maps A, B, and so on that have this usual homology condition and expansion for each one of them? That's an open question. And if you could do that, you would achieve some of the quantum conjectures that I would like to achieve later on. So there's one last classical thing I want to mention. So what this lets you do is this lets you check whether you're in the code space in a robust way. And one reason why this is of interest in classical computer science is something called the PCP theorem. It's called the probabilistically checkable proof theorem. The high level, the intuitive picture of what this means is there's a giant proof. How do you verify it's correct? Well, you just verify that each line follows from the previous line. It's kind of like with a repetition code. That's like this method of verifying the repetition code. You verify that x1 equals x2, x2 equals x3, and so on. And if they're all equal, you're in the code. With the proof, if every line is correctly derived from the previous line, the proof is correct. So you have to read the whole thing. Wouldn't it be nice when you're grading papers if you could just open it to 3 random points and check for those for mistakes. The PCP theorem says you can encode a proof in this way. So let me be a little bit more formal about it. Suppose you have a 3-set instance. So let me write this as follows. Phi of x is 1 over m is an average of phi sub I of x. So each phi sub I maps is either 1 or 0. It's 1 if clause I is violated, and 0 if satisfied. Just to back up a step, 3-sat, there are m clauses, each one of which depends on 3 bits. So it's some just simple formula of 3 bits, and you'd like all the clauses to be satisfied. And there's some setting of the bits which satisfies them and other settings which violate them. Doesn't matter exactly what those settings are. But we'll just assign a cost of 1 for every violated clause and 0 to every satisfied clause. So this function phi of x represents the fraction of satisfied clauses. And it's NP complete to determine whether this minimum is either equal to 0 or greater than 0. In other words, does there exist an x which satisfies everything? That's the classic NP-complete problem. And you can see, to check whether something satisfies everything, at least naively, it looks like you just have to read all of the clauses. If you just pick one at random, let's say there are m clauses, and you pick one at random, and only one of them was violated, the chance that you pick that one will be small. It'll shrink with the size of the system. Whereas the PCP theorem says that it's NP complete to distinguish these two cases, minimum over x phi of x is either equal to 0 or greater than some universal constant. Maybe even better than 1/10, but you get the idea. There's some universal constant, and so I know that either all of the clauses are satisfied or 1/10 of them are unsatisfied. And if 1/10 of them are unsatisfied, I'll notice that just by picking one at random. I have a 1/10 chance of noticing that. So that seems like it should be way easier. And the PCP theorem says, no, this is still NP complete. In other words, if I have any formula of this form, I can reduce it to one of this form. So if I have a proof of something, I can translate it into a proof where the errors are readily apparent. Where if I just pick a clause at random with 1/10 chance, I will notice an error. So this is a great triumph of theoretical computer science. And what it means is that this problem is hard to approximate. So if I want to know, if I'm given a 3-sat formula, approximately how many clauses are satisfiable, that point is even that is hard. Even just to approximate very crudely how many clauses are satisfiable, to distinguish these, this is pretty far apart, 0 versus 1/10. Even that is NP complete. And people have gone on to show that for many other constraint satisfaction problems, it's NP complete to roughly approximate them. Or for something maybe more appropriate to this week, let's say you have the operator norm from the L2 norm to the L4 norm. That's something I've studied a lot. To approximate that can be shown to be hard. So it's easy to show that to calculate it exactly is hard, but you can even rule out efficient approximations by using these kinds of techniques. OK, so let me talk about quantum things now. These are all classical codes. Of course, you can always make them. Right, so let me define a quantum code. For a quantum code, physically what we'd like to do is take k qubits and encode them into n qubits in a way that the quantum information is protected. So that if I lose some of the qubits or someone applies some arbitrary error to them, I can still recover the original information. So mathematically, I have C is now a subspace of the space of n qubits. And the dimension of C should be 2 to the k, that means I have k encoded qubits. And there's a notion of distance also, which I'm not going to precisely define, but roughly it means if I want to go from one code word, one encoded state to another one, I have to touch at least d positions. I can't do it with just touching a few. I have to touch d positions. And classical mechanics should be a special case of quantum mechanics. How can we get classical codes from quantum codes? Well, just in the linear case, let's say I have checks A1 through AM. I can define my code space to be the ground space of sum from I equals 1 to m, minus sign out front, sigma z to the a sub I. Okay, so what do I mean by this? So if I write, sigma z to the 1, 0, 1, 1, what I mean is sigma z tensor identity, tensor sigma z, tensor sigma z, right? So if this is a vector, it means wherever there are ones, I put a z in that position. And you can see that, so the eigenvalues of this product of sigma z's are going to be plus or minus ones. And when you put the minus sign out front, that means that you want the ground space is going to correspond to the +1 eigenstates of this. And it's going to be basically the strings that satisfy the parity constraint way up there. Their inner product with AI should be 0. So this board, this board is fixed. I see your point. So good. let me erase over here then. In general, we can define a quantum error correcting code. We can think of it as the ground space of some Hamiltonian H, and it'll be convenient for me to normalize it. And it's often convenient. This is, to define the ground space, I don't care about what the overall norm is. It's still convenient to talk about each local term as having norm at most 1. And and for the same reasons that a classical code would like each term to check only a few bits, it's convenient to have each hi have constant locality. If anything, this is more important in a quantum system, because to perform a quantum error correcting code, to check whether in the code space we have to measure all of these h sub I. And the fewer qubits we have to interact, the better. So and I guess one other thing which we typically have is we typically have all of these operators commute. It's not strictly necessary, but it makes a lot of things easier, both the analysis and the implementation of these codes. So one important family of codes due to Kataev are called homology codes. And this is one of the things I just erased. So let me write it again. Let's say you have maps. Let's call this A, B. We'll write the Hamiltonian to be minus the sum over the vertices. Oh, sorry. So let's say you have some kind of homology like this, some F2 homology. We'll take n, the number of qubits, to be the number of edges. Okay? And then we'll assign check terms to each vertex and each face. So we can write h to be minus the sum over vertices sigma x to the AV minus sum over faces sigma z to the B transpose F. And maybe for a normalization, let's divide by the total number of vertices and faces. So what does this mean? For every vertex, we apply AV to it. That means you take all the edges incident upon that vertex, and you do a sigma x on that edge. For every face, you look at all the edges around that face, and you do a sigma z on that face. On that edge. So both of these are terms that live on the set of edges. And you can see if you just had one of these, this would be a classical error correcting code, a classical parity check code. But we essentially want to do parity checks in both the z and the x basis. And you can show that this code has a dimension. So let me be clear about dimension. This is the complex dimension of the code is 2 to the F2 dimension of the homology space, the kernel of B divided by the image of A. In other words, the non-trivial loops, the loops that are not themselves the borders of sets of faces. And this has the property, this code or quantum codes in general, that ground states are highly entangled. So they cannot be written as products of local terms. But it's more than this. So when we talk about in the earlier talks this week about non-local correlations, there was often the talk of two-party entanglement, right? And so with two parties, it's pretty clear when something's product or entangled. But if you have n qubits, how should we think about n qubits being entangled? It could be that those n qubits correspond to n over 2 EPR pairs, in which case it's entangled, yes, but the entanglement is sort of local. If you sort of zoom out a little bit, it doesn't look very entangled. So quantum error correcting code states, if they're really fully making use of the n qubits, they should be somehow genuinely entangled across all of the systems. So this is how they should protect against local noise. So I have not formally defined distance, and I realize that, but let me just say the distance of these homology codes is the minimum over x in the kernel of B minus the image of A, the norm of x, or a similar term, z in the kernel of A transpose minus the image of B transpose, norm of z. So in other words, if all of the whatever the smallest non-trivial cycle is, that tells you the distance of the code. This is called the systole, if you're familiar with that term. So if that is large, these codes have large distance, which means you cannot access the protected quantum information without touching many qubits. This is one notion of many-body entanglement. And the kind that Lior and I discussed in our paper, which I'm going to tell you about the results of at a very, very high level, is that the states are what are called non-trivial, which it's easier to define what's trivial than what's non-trivial. So let me put it like this. So we say that a state psi is trivial if you can prepare it let me just write it like this. Psi is u d d minus 1, u1, 0 tends to n. So you start with the all 0 state, and you apply d unitaries, and each ui is product of 2 qubit unitaries on disjoint pairs. This is also known as a depth d quantum circuit. So you have d layers. In each layer, you can do as many 2 qubit gates as you want, but they have to always be on different pairs of qubits. So you can do n over 2 different 2 qubit gates in each layer. And if you can do this in d layers, where d is some constant, then we say that the state is trivial. So for example, n over 2 EPR pairs is, you can prepare that in a constant depth. No matter how big n is, you can just do these parallel operations to prepare all of the EPR pairs. But the ground state of these, the code states of these homology codes, you can show are not trivial. You cannot prepare them in a constant depth from product states. And there are two reasons why being trivial, a trivial state is relevant. One of them is in condensed matter theory. So there's been this effort to classifying classifying phases of matter. And we say the two phases are equivalent in the thermodynamic limit if you can relate them with a constant depth circuit. Or there's a few equivalent notions of this, but this is one reasonable way of saying it. So if as n goes to infinity, if there's some constant, and I can in constant depth, or equivalently constant time of time evolution, go from one state to another one, then these are essentially in the same phase. If I can't do that, then these are in different phases. So these trivial states correspond to things that are in the trivial phase. They're related by a constant depth circuit to a non-interacting, the ground state of a non-interacting Hamiltonian. So that's one reason why this is relevant. The other is for complexity theory. There's a quantum analog of the PCP theorem, which argues that it's hard to approximate the ground state energy of local Hamiltonians. And if this is going to be true, then we must have local Hamiltonians where their low energy states are not trivial. And the reason for this is that if you have a trivial state, it's computationally easy to estimate local observables. So if I want any observable on a few sites, applying this constant depth circuit doesn't blow up the locality by that much. So on a classical computer, I can efficiently estimate the value of that local observable. So if you want something which is going to be hard for classical computers to estimate the energy of, you need things that are not trivial states. So what does our work show? We have a few, so I think I'm not going to write it down, I'll just say it. The first thing we do is we give a criteria to show that a state is non-trivial. So, and the criteria, I won't write it down, but I'll draw it. The criterion is the following one. Suppose you have a state, let's say a code state, and you'd like to show that it's non-trivial. Then what we prove, so how can you show that? There's a lot of low-depth circuits. How can you rule out all possible low-depth circuits? What we prove is a geometric way of showing this. We say, suppose you measure the state. Then you get a distribution, a probability distribution over n-bit strings. And this distribution, let's say this is a space of n-bit strings, is going to look like some kind of cloud. What we show is if this distribution has a small cut, so there's some, in other words, you can partition it into two sets that are far apart, and the amount of mass between them is not very much. In other words, if they are not correspond to a not very expanding distribution, then this cannot, then the state is non-trivial. So a trivial state might be something like the uniform distribution, where there's no way to cut it without having a lot of things cross it. A non-trivial state would correspond to something like an error-correcting code, where you have two subsets that are far apart. So the first thing we do is we give this kind of general connection between error-correcting codes and non-trivial states, showing that if you have the kind of partition that you have in an error-correcting code, that will prove that the state is non-trivial. The second thing we do is we come up with a homology code, a new kind of homology code based on using expander graphs, such that even if you delete a constant fraction of the qubits, the state remains non-trivial. So things like the toric code, the state is non-trivial, but if you delete a constant fraction of the qubits, it becomes trivial. We give something where even if you delete a constant fraction of the qubits, the state remains non-trivial. And I don't have time to go into the construction, but I'll say it's based on combining these homology techniques with expander graphs. And expander graphs also have this kind of, they're very robustly connected in the sense that if you delete a constant fraction of vertices, still most of the remaining vertices form a smaller expander graph. So I know I've been vague at the end, but I think I'll stop here and take any questions. Thanks for your attention.
No, thanks. So other questions?
What's the 3 regular? I mean, why is it 3 regular or not?
I want it to be 3 regular because actually any kind of regular expander graph would work. So for example, I could take the complete graph as well. And just, pick the complete graph would also have this property. I guess the reason to make it 3 regular is so that it's constant degree. And the reason why constant degree is important is when it comes to our construction, which I did not explain yet. So in our construction, where we give a quantum code where if you delete a constant fraction of qubits, you get something that's a non-trivial state, we base it on having an expander graph, and we also need that expander to be constant degree. And so when I think of expanders, I often want them to be constant degree. But you're right that to be a locally testable code, you could have also used the complete graph, and that would have also worked.
But does that make the decoding worse? I mean, is it good to have a low regular degree?
It depends on your scenario. So if you're just choosing a random edge, it doesn't matter very much. If you are going to list all of the constraints, maybe you prefer to have the total number of constraints be smaller. So it depends on your setting whether or not it's costly to have a very massively redundant set of constraints or not.
Good. So more questions?
Yeah, just want to make sure. So when you talk about the ground state, you mean actually a ground state space, right? So
yes.
The code space would be the ground space.
That's right.
Okay.
That's right.
But then how to prepare this kind of Hamiltonian? Is that easier or?
So this is a place where the reason why homology is a natural thing to do here is because if each vertex borders a constant number of edges and each face borders a constant number of edges, then each term in the Hamiltonian will just touch a constant number of qubits. So that's why homology has been an attractive way to develop error-correcting codes. And now, actually, this brings an answer back to Felix's question, which is, suppose A is going to be an expander graph. For the purpose of being a classical locally testable code, I could have used the complete graph. But now, if I want to make it into a Hamiltonian, I would really prefer that it's a constant degree graph, because I want each term in the Hamiltonian to touch only a constant number of qubits. So how easy is it to do it? Well, I mean, experimentalists would say even interacting 4 qubits is no picnic, but at least 4 doesn't grow the size of the system. So it's not trivial to do, but I think it's closer to being reality than most other error correcting codes.
Okay, yeah.
So just following up on that a little bit.
Yeah.
I've seen that with the forward code, which also has some similarities to this. There's sort of like 2 ways to do it. One is you can have this Hamiltonian that encloses the ground state, and the other one is you actually apply measurements on input S and essentially do active error correction. And so I was wondering if this Hamiltonian also has sort of this analog in that you could actually just perform active operations on each of these small qubit sets that would be equivalent.
Yeah, I mean, the Hamiltonian, you don't actually ever need to evolve according to this Hamiltonian. It's almost just like a mathematical way of specifying the ground state and of telling you how many of the constraints are violated. So I think for any code, you can do it, you can imagine either which way. You can either imagine that these terms are things that I'm going to individually measure, and the fact that they commute is particularly great because I can measure them in any order. Or you can imagine that there's a physical system with this Hamiltonian, it's in contact with a cold bath, it's relaxing to its ground state. For any code, you can, either of those pictures is okay. Yeah.
Can I just comment on that?
Mm-hmm.
We'd still need a decoder in order to know which of the ground states that you're in, otherwise you're going to wind up in a mixture.
Right. So that's true. So that's important. I've not really gotten into the complexity of decoding also. So like when you, a whole other story.
Do you have a decoder?
I think that, so our code, which I did not get around to describing, is based on a construction by Tillich and Seymour. And I think that their other work with Leverrier gives a decoder. We didn't come up with it, but I think it's just in the literature. That one should work.
Okay, so no more questions. So let's thank Aram again.